So for this problem, a mixture having a molar analysis of 50% nitrogen, 30.5% carbon dioxide, and 19.5% water vapor enters a turbine at a given temperature and pressure with a mass flow rate of 3.3 kilograms per second and expands isentropically to a pressure of 100 kPa. The turbine operates at steady state, and kinetic and potential energy effects can be ignored. Determine the temperature at the exit. So we want to find T2, and then the power developed by the turbine, Wdot. Okay, so the bottom line is, for solving for the exit temperature, we're going to basically use a second law, an entropy analysis, entropy balance. And to solve for Wdot, it's the first law for the control volume around the turbine, and it's an energy balance. So entropy, energy. First law, second law. All right, so we just make a quick sketch. Maybe I'll do it over here. Here's my turbine. We have inflow at 1, outflow at 2, and Wdot power coming out. We're going to have a control volume analysis, CV. For that control volume, the Qdot is equal to 0. The turbine operates at steady state, and you take a look at it, and it expands isentropically. Okay, how do you expand isentropically? Well, if you expand sigma dot equal to 0, no entropy production, and it's adiabatic, so it's reversible and adiabatic, you get that S1 is equal to S2. It's isentropic expansion. So that's what we're doing. Okay, so what we want to do is first do a set up a table to help organize the calculations. So for the table, we have each component. We have the nitrogen, we have the carbon dioxide, and the water vapor. And we might as well look up the molar mass of each. The molar mass for the nitrogen comes in at 28.01, carbon dioxide 44.01, and 18.02 for the water vapor. Units of kilojoules, not kilojoules, units of kilogram per kilomole. All right. We also put in our Y's, mole fractions. So this is 50%, 30.5%, and 19.5%. Okay, you do the sum, it's 100% good. Now what we do is we calculate Y times M, put it in this column, this column, this column, and when you sum Y times M, you'll get the mixture molar mass, and for this problem it comes in at 30.94195. So the molar mass of the mixture is 30.94195 kilograms per kilomole. All right. So if you wanted to go back and forth between the mass flow rate and the molar flow rate of this mixture, you would take the molar flow rate and multiply by the mixture molar mass. Okay. Or since we have the mass flow rate, the molar flow rate is the mass flow rate divided by the mixture molar mass. And when we do that, we find that our mixture molar mass 0.10665 kilomole per second. And then if you wanted to calculate the n dot of each component, I, you just take the mole fraction times n dot of the mixture. Because this is all, there's no, typically the book doesn't have a subscript for the mixture, it just leaves it off. So just leave it as the total molar flow rate. Okay. Now, what we're going to do is we're going to have a second law analysis to find T2. Okay. Well, what does the second law equation look like for this control volume? Well, it's steady state, so let me write it out in general here. 0 is equal to Q dot divided by TB, but we're going to assume it's no heat transfer and reversible, hence that's how you got its isentropic expansion. And then we have a couple ways you could put the n dot of each component times its inlet molar entropy minus its exit molar entropy, okay, plus sigma dot, and then you sum over all of those component i's. Well, if it's reversible and adiabatic, that's how you got its isentropic. Then what we have is we have the sum of the S bar 2's minus S bar 1's for each of those components, multiplied by the molar flow rate, is equal to 0. All right. Basically, you could put out here n total times the yi gives you the n dot I, or this is n dot times yi gives you n dot I. Here I should, well, it's written right here. So I'm just then canceling off the n dot out of the equation. So there you go. So how do we do this? Well, we have to take and calculate the sum of the mole fraction. And how do I calculate the change in entropy? Well, it'd be the low pressure entropy at the exiting temperature minus the low pressure entropy at the inlet temperature of 900 Kelvin minus the R bar natural log of P2 over P1. Okay, maybe I should have used a different bracket there. Go like this. The sum of y's times those delta S bars must equal to 0. Well, we don't know this temperature T2, hence we can't calculate the S bar not at 2 out of the table. So what do we have to do? We guess and iterate T2 such that this equation is equal to 0. All right. So to help us, let's go ahead and evaluate the S bar not 1. Now, as a reminder, that's at our temperature of 900 Kelvin. This is our inlet temperature T1. Okay, so let's go ahead and put those values down for S bar. 224.647, 263.559, and 228.321. Those are all in kilojoules per kilomole Kelvin. And where did they come from? Table A23 in our textbook. They account for temperature-dependent specific heats. They're all on a molar basis. Okay. At this point, you have to guess T2. So at first, I'm going to do this. I'm going to guess T2 is equal to 500 Kelvin. So if we put in 500 Kelvin, then this value of S, let me put it here, S bar not at 2 for nitrogen comes in at 206.63. For the carbon dioxide, it comes in 234.814. And for the water vapor, 206.413. Okay, now you take the change in those S's and add to it this R bar natural log of P2, which is 100 kilopascal. I'm sorry, P2 is 100 kilopascal divided by P1 600 kilopascal, so 1 over 6. And then you can calculate this. And let me just kind of draw this out. This is S bar naught. No, I'm just going to go ahead and include that natural log minus S bar 1, S bar 2 minus S bar 1. So at guessing a T2, you find this is negative 3.12. Then it's negative 13.85 and negative 7.01. You then multiply by y's, so I'm going to put a y times S bar 2 minus S bar 1. Make those products of the mole fraction times the change in the molar entropy. You do the sum. This comes in at negative 7.1511. It's not equal to 0. So what do we have to do? We have to go and change T2. So when T2 was equal to 500 Kelvin, this is not equal to 0, but is equal to negative 7.1511. Now you change T2, maybe even make a table over here and say this is my value of T2. This is my function that I'm trying to drive to 0, and it's a function of T2. And what we found was when we put in 500, this comes in negative 0.1511. Well, let's try 700. Just repeat the process. When you put in 700, this comes in at 5.1243. Well, now you do root finding. This is just numerical root finding. Let me just give you a quick function between 500, 700. When the function was evaluated at 500, it came in at down here at negative 7.15, etc. And then when it's 700, it was positive 5.12. You draw a straight line, and you find where that should hit the x-axis, where the function should be 0. And using these two pieces of information, the next best guess is 616.5. All right, 616.5. So when you stick in 6.615, it comes in 0.3891, a lot closer. So what we do is we use these two pieces of information, one below and one above, to get the next best estimate. Do a linear interpolation again to try to find it. When you do that, you're going to come in with a value. The next best guess is 610.5. When you put in 610.5, it comes in at 0.0299, and I think you get the point. So what we find is it quickly converges to 610. At 610, let me see if I can plug that value in. 610, it is a bunch of zeros. 0.0000682. Boom. So that's our converged. As you can probably guess, I made up this problem and adjusted the mole fraction such that I would get a nice easy number like the final answer for part A. T2 is 610 Kelvin. We could box it. So T2 is equal to 610 Kelvin. Boom, done. All right, what about the power developed by the turbine? Okay, I need more room, so we'll scoot down. And we already said that the power developed by the turbine would be the sum of the molar flow rates of each component times the inlet molar enthalpy minus the exit molar enthalpy. Where did that come from? Energy balance. And we can just put the total molar flow rate times the mole fraction of each component times the change in the enthalpy of each component. All right. Maybe what we could do also to help organize, we still stay with our table of nitrogen and carbon dioxide and the water vapor, and we just add what is H1 bar. Again, that's evaluated at T1 of 900 Kelvin in units of kilojoules per kilomole. And we'll go to the table and we find H1 is 26,890, and then 37,405 and 31,828 for those three components. And then at 610 Kelvin, we find H bar 2, same units. So this will be 17,864. This will be 22,754 and 20,765. So what you would do is maybe just put H bar 1 minus H bar 2, then multiply by Y for each of these, get three values, do the sum. Then you take that multiplied by the molar flow rate, and W dot comes in at a final 1188 kilowatts. All right. Well, I hope this was helpful. Thank you for your attention.